Good morning, everybody. Been a while since I did one of these, but I thought it might be helpful to go through some conservation of energy problems that deal with elastic potential energy and also deal with thermal energy. Okay, so let's take a look at this first question here. So, a low friction cart with a mass of 0.25 kilograms travels along a horizontal track and collides head-on with a spring that has a spring constant of 155 newtons per meter. Okay, so that's our K. If the spring was compressed by 6 centimeters, so that is our X, in centimeters, which we convert to meters, how fast was the cart initially traveling? So we're looking for the final speed of the cart. So anytime we have energy that is changing from one type to another, okay, we are always going to be using conservation of energy. Okay, the energy at the beginning is the same as the energy at the end. So anytime you're dealing with going from one type of energy to another, or one type to multiple types, or multiple types to one type, okay, you're always going to start with the conservation formula. So the total energy at the beginning equals the total energy at the end. So at the start, the only thing the car has is velocity, right? So this, low friction cart is kind of your clue that friction is not going to play a role in this question. Okay, so at the start, we have only kinetic energy, right? So we have only kinetic energy that we're trying to find. And at the end, okay, all of that gets converted into elastic potential energy. So the cart's going to go into the spring. It's going to compress the spring until it stops storing all the energy in the spring, at which point the spring will release and transfer the energy back. So we have 1 half mv squared equals 1 half kx squared. Okay? Now, normally in these questions, when we do conservation problems, we're able to cross out the mass. That's not the case whenever we have a spring, because there's no m term in the elastic potential energy equation, so we can't cross it out. In this equation, though, we do have half and half on both sides, so we can cross that out. Anytime we can make our lives a little easier, we always try to do that. Okay, so now we just fill in our numbers, and we are just going to be solving for v squared to see what we get. Okay, so we expand these, we get 0.558. We divide by 0.25 to get a 2.232. We take the square root, and we get that our final answer is approximately 1.5 meters per second. Okay. So this is a fairly simple case of this type of problem, right? We're dealing with conservation of energy, and we're turning kinetic energy into elastic potential energy. So we're going from something that's moving to storing all of that movement in the compression of a spring. Okay. Let's take a look at one that's a little bit more challenging. Okay. So a spring having a force constant of 520 newtons per meter is placed on a plane inclined at 67 degrees to the horizontal. The spring is compressed by 0.4 meters. And a 2 kilogram mass is placed on it. The magnitude of the frictional force between the mass and the plane is 4 newtons. Find the speed of the mass after it moves 1.3 meters up the plane. So this problem, we're dealing with a lot of stuff. We're dealing with height, we're dealing with we're dealing with spring, so we have elastic potential energy, we have gravitational energy, we're dealing with movement, we have kinetic energy, and we also have mention of friction, so we also have thermal energy. So this problem kind of has everything. So we have a ramp, we have a spring, the spring's been compressed, mass is placed on top of it, and then it's released. The spring, right, pushes the mass, and the mass will slide up row. So again, we have changing types of energy, and anytime we have changing types of energy, right, we're using conservation. The total energy at the beginning equals the total energy at the end. Now, at the start, the only type of energy it has is elastic potential. Now, technically, right, when you have the spring all the way compressed, we are off the ground. But whenever we're dealing with height, we can choose a reference level. So where the spring starts fully compressed, I'm going to set that as my 0. And then gravitational potential energy is based on the change in height, not just the actual height. So the height from a given reference. So where the spring is compressed, I'm going to say that's the bottom. That's H equals 0. And so the only type of energy I have at the beginning is elastic potential energy. Okay? As it shoots up the ramp, right, it's moving. So we have kinetic energy. It's at a height. So we have gravitational energy, and friction is involved. So we also have thermal energy. Okay, so all of the energy stored in the spring gets transformed into these 3 types of energy. Okay. So we have all of these values here. So we know we're solving for the speed, right? That's the thing that we're trying to find. We have K, we have X, we have M, we have G, we have the force of friction, we have the distance that it moves up the ramp. The only thing we're missing here is H. So in order to solve this problem, I'm going to have to find H. So to do that, I just take a look at my triangle. And I'm just going to draw a little one here for reference. So it moves 1.3 meters up the ramp. The ramp is at an angle of 67. So this side over here is going to be my height. Okay? So this is just going to be sine of 67 equals opposite over the hypotenuse. Okay, so I run that through my calculator and I find the height. Okay, so now I have everything I need to solve this problem. So in problems like this, it's very important that you set it up properly. And when you're calculating it, I'm probably going to show more steps than you might use in your own solution. But there's lots of numbers and lots of parts, so it's very easy to make a mistake. Okay? So always be careful when you are solving these kinds of problems. Okay, so 1/2, when I do calculations, I have to replace it with 0.5. So 520 times 0.4 squared equals 0.5 times 2v squared plus 2 times 9.8 times 1.1967. So taking, again, 4 decimal places for accuracy, plus 4 times 1.3. Okay. So the left side here, when we put this all together, okay, that will give us 41.6. Okay. 0.5 times 2 is 1, so that's just v squared. Okay. When we multiply these values together, okay, we get 23.4553, and 4 times 1.3 gives us 5.2. Okay. So I'm going to rearrange this equation a little bit. So v squared is going to be 41.6 minus 23.4553 minus 5.2. So I get 12.9447. Okay. I take the square root, and I find that the final speed is approximately 3.6 meters per second. So I was able to, using the information question, find the final speed. Okay? So this question kind of, has all the different types of energy in it. We have elastic potential energy, gravitational energy, kinetic energy, and even thermal energy from friction. Okay? So you should always pay attention. Make sure you know which side of the equations are on. This second line right here, where you set everything up, is probably the most important for solving these problems. So hopefully that helps you understand how we can combine the conservation of energy from grade 11 with the new concepts of thermal energy and elastic potential energy.